Okay, so welcome everyone. Today we're very happy to have Djordje Radicevic from Brandeis University, and he'll be talking about comments on the lattice-continuum correspondence.
Okay, hi everyone. Thanks for having me. And please let me know if there is anything unclear or if there are any technical issues. I guess like most of you, I'm also new to giving talks via Zoom and without seeing my audience, etc. So please don't be afraid to say if something is unclear or if it's difficult to hear me or something like that. So let me start with the motivation for my talk now. You can see the title, and it's based on these two papers from December of the previous year, and there's a lot of work in progress that I may or may not touch upon depending on the questions that are asked. So I'm going to talk about an old subject, the dichotomy between lattice and continuum quantum field theories. So even though this is something that people have discussed in many ways for years, I think I will make some observations about this and that are, as far as I know, fairly new. And the point of view that I will advocate is something that I have definitely not seen in the literature. So I think it will be of interest to many people, hopefully. And the talk will be pretty formal, which I think is okay for a mathematical physics seminar, but it will be quite elementary. It will really deal with very simple quantum systems, and in principle, everything can be understood simply. There's nothing too deep or difficult to define going on here. So with that said, let me start. So let me first talk a little bit about what I mean by continuum and lattice quantum field theories, just to set the expectations right. So when I talk about continuum quantum field theories, I mean I'm talking about something. I'm talking about a diverse set of theories, a diverse set of concepts I think a fair way to represent them all is to say that these are certain rules or assignments of operators to manifolds or similar geometric spaces, coupled with consistent rules for computing expectation values of these operators. And these rules may be special, may depend on particular structure of the manifolds. They may take into account specific symmetries, saying that the operators have to be in particular representations of particular symmetries, etc. Different axiomatic frameworks exist to define continuum quantum field theories, but I think this is the kind of abstract statement that should encompass most of them pretty fairly. So this includes topological quantum theories, this includes conformal field theories, this includes perturbative approaches to QFT that we are familiar with from Peskin and Schroeder, etc. So all of these fall under this first category that I'm going to talk about. On the other hand, when I talk about lattice quantum field theories, I will mean something rather specific. I'm going to imagine that I have a finite graph, possibly very, very large, but still finite, and that I have a Hilbert space, a finite dimensional Hilbert space associated to its components, sides, edges, faces, etc. And that my set of states, that my full Hilbert space is simply a tensor product, possibly a graded one, of all of these finite dimensional spaces that are associated to components of a graph. Instead of graph, I will say lattice from now on, but you can just generically think of it as a graph. And all the dynamics, all the expectation values are essentially specified by knowing what the Hamiltonian is. So basically, it's a particular operator that acts on this tensor product, and it's ideally respecting some kind of locality, so that it only couples things that are in some sense near each other on the graph. And in this context, it can just be thought of as a huge matrix, nothing else. So A lattice QFT in my definition here is something that's fully regularized. Its corresponding set of operators is a type 1 algebra. They're just matrices, etc. And in that sense, it's perfectly straightforwardly defined. There are no terrible ambiguities here. Good. And so I should also comment on why we actually care about both of these. And I would say that there are pros and cons for both approaches to QFT, for both ways of thinking about a QFT. So there's almost no need to glorify continuum quantum field theories further. I mean, of course, thinking about them has led to amazing mathematical insights. We have been able to prove a lot of interesting things, to discover a lot of new interesting ideas that I have no need to even review. And of course, on the other hand, thinking about continuum quantum field theories has also allowed us to devise powerful ways to talk about our own world, to predict results of experiments and to understand what makes up our own matter and so on. On the other hand, lattice field theories are also interesting. They allow conceptually different types of probes, that may not be amenable to analytic treatment as continuum theories are. So, for instance, if we have a lattice formulation, we can imagine putting it on a computer and simulating it, or we can imagine simulating it in an actual experiment, with spins or with atoms or with cold atoms or with or in laser lattices, etc. And we can do experiments, numerical or physical, to actually figure out what's going on without actually being able to solve the theory. So that's one reason why lattice theories are interesting. And another reason is that sort of formally, they also are, as I mentioned, perfectly finite. You have complete, full non-perturbative control over everything. It might be difficult to compute things, but at least everything is perfectly clearly defined. You don't have to worry about what's universal, what's not, etc. And so that last reason is kind of what drives me to think about lattice theories. Okay, good. So that's the basic aspect of the correspondence, of the distinction between the two that I want to talk about. And now I should say something about the correspondence between them. We expect that these things are possibly describing the same set of theories, maybe just from very, very different points of view. And certainly some physical phenomena are easily seen in both. Perturbative behavior of free theories is very often easily seen in both formulations, in both frameworks. But there are certain notions that are much more natural in one framework than the other. So, for instance, it's much easier to talk about chiral theories in the continuum, and it's much easier to talk about confinement on the lattice. Confinement is much more natural somehow, for instance, in lattice gauge theories, whereas it was a shock in the continuum. And so that brings me to the puzzle that I have been thinking about for a while, and that has also been a subject of much discussion for the last 50 years or more. And the question is there a lattice formulation of every continuum quantum field theory? Meaning, if I give you a continuum theory, pick your favorite theory, let's say n equals 4 super Yang-Mills, for instance, or something even fancier, or some CFD specified by its data, by its conformal data. Do we know, or how can we get at a lattice formulation of it? How can we be sure that we can give it a full, completion, a full regularization, while still making sure that we will get the right continuum properties? So typically, the way this is the intuition that we built for doing this kind of stuff says that we imagine having a lattice theory we imagine the lattice being very large. Sometimes this is called taking the lattice spacing to 0, but I will try not to use that language. And we imagine that we tune the couplings of the lattice theory. We don't expect that every lattice theory will correspond to a continuum one, but we expect that if we are near, ideally near a second order phase transition, or in some other auspicious regime of couplings, we should actually be able to get a correspondence between continuum and lattice theories. So that's the vague intuition that what's needed is to be in the right parameters part of the parameter space and to take the lattice to be very large, and that's roughly the intuition that most people have. So and indeed, I will today talk about how some properties of continuum theories can emerge from lattice theories in a way that's slightly going beyond what I just said, what this standard intuition is. And I will describe this more on the next slide. But essentially, what the bottom line is that I will sort of extend the kind of thinking that we have been thinking that has been standard, and I will talk about how certain ubiquitous properties of continuum field theories can indeed at least emerge, at least approximately, from lattice theories in a very precise way that is, as far as I can tell, relatively undiscussed in the literature. And just to be concrete, I will specifically care about, in this talk, about reproducing operator product expansions, about understanding operator product expansions on starting from lattice theories. This is something that's on the face of it kind of unusual on the lattice. You know, an operator product expansion in a continuum theory says that as two operators get close to each other, you can replace them by some linear combination of other operators. This kind of doesn't make sense on the lattice because your operators can't just get arbitrarily close to each other. They're either on different sites or different components of the lattice, or they're on the same one. And so, you know, if they're apart from each other, then there should not be any, you know, they should be acting on different different components or different factors of the Hilbert space. And in principle, they should not be talking to each other. So the question is, how does one start from a nice free theory, let's say, and get an operator product structure straight from the lattice? So I will describe that. That will be the quest in this talk. And along the way, it will also become clear how the Kac-Moody algebra arises. How, you know, this is going to specifically, it's going to be a U1 level 1 algebra, but generalizations will be relatively clear. And it's another example of how you can see something that is very, you know, well known, well loved in the continuum, a current algebra, and how it can be shown to at least approximately be realized on the lattice, and how in a certain limit you actually see the right continuum object emerge. Yeah, I want to once again emphasize that I'm open to taking questions. So if you're confused or if you are angry or you want to more clarifications on what I say, please feel free to ask. So this is the last part of the introduction. I'm going to talk about a little bit more of the historical context on how this how people have thought about realizing continuum phenomena on the lattice, and I will give slightly more details on how what I'm doing is different. So as you can see on the slide, the question of how to put X on the lattice has been popular for years. Some of the most interesting questions, some of the questions of greatest interest are listed here. So people have tried very hard with some success to put, let's say, supersymmetric theories on a lattice. That's very difficult because the structure of supersymmetry is inherently tied to there being, let's say, infinitesimal translations, which are not something that you ever see on a lattice. So, and there are other issues that arise as you go down this list of possible x's. And as I said, part of the reason why people cared about this was because they wanted to simulate this, to reach the non-perturbative regime by putting the theory on a lattice and just doing a Monte Carlo simulation or something like that. Now, I want to emphasize that thinking about simulations is great, but then that also assumes that you can efficiently simulate things. I in this talk will not care whether you can efficiently simulate things, whether there's going to be a sign problem or something like that. I just want to see how formally specific concepts emerge from the lattice. So that's one caveat. I will not care about how to efficiently simulate x, but I will care how to get x. And in my case, x will primarily be the operator product expansion, which is something that, aside from a few recent tensor network studies, has not actually taken that much, has not actually captured that much interest from the community that asks such questions. And I should also say that there's plenty of no-go theorems and no-go folklore, saying that in general we should not expect too much. We cannot have exact chiral symmetry coupled with a lot of other, a few other natural requests, as has been proven by Nielsen and Inomiya. So there is an actual theorem saying that you cannot have quadratic fermionic Hamiltonians which have exact chiral symmetry and like the right kinds of locality, etc., etc. So we know that it's not easy, and we know that we should not expect everything that we see in the continuum to be on the lattice on the nose. We should be ready to make compromises. We should be ready to approximate things. And this is the kind of thing I will be proposing here. And as I already explained in some detail, and concretely, I will be working with fermions, with free fermions for simplicity in 1+1D. And I will construct an algebra of lattice operators that does have a natural OPE structure. It's going to be a subalgebra of the entire one. And it's sort of chosen to precisely give you the right OPE structure in some very simple way. And the thing that I need to emphasize, the thing that I think is different from most other approaches, is that I will actually not even get the right OPE structure just by taking the lattice to be large, or just by taking the lattice spacing to be 0 in the colloquial parlance. It actually turns out that you need another cutoff. You need another regulator that's going to that is going to control how well you can approximate the continuum OPE structure. So one of the upshots of this talk is going to be that you may need to have more than just a single cutoff. You may need to think about a hierarchy of cutoffs in order to reproduce the right continuum behavior. And I will make this extremely precise. That's kind of the point of the talk. But this is the takeaway idea or one of the takeaway ideas I want to emphasize. And I want to also stress that this was kind of known. It was never, as far as I know, this kind of need for other cutoffs has never been worked out in any generality, but it has certainly been known to some practitioners, and I can list some references later on if people are curious, where people have kind of intuited that, oh, we need something infinitesimal, but it can't possibly be the lattice spacing that would screw us up. So there have been precursors in the literature, but I think that this story has never been told before. Okay.
Can you precisely show some kind of no-go statement or result if you only have a single cutoff? Or is that just built into the formulation of the problem?
I think I haven't formulated this as a theorem, but I'm pretty sure you can show that. Yeah, I haven't thought about what are the right, the minimal assumptions and so on, but I'm pretty sure there is at least something that we can phrase as a no-go theorem there. Yes. Okay. Yeah, like if you try to construct, let's say, the Kac-Moody algebra directly from the lattice, you can kind of see why it fails if you have a single cutoff. So I'm pretty sure we can we can formalize this, but I have not tried to do so.
And just out of curiosity, those no-go results you mentioned before, the theorems and folklore, what kind of ideas did they use to say that you can't get stuff on the lattice?
So they essentially used things like, well, in the specific case of Nielsen and Ninomiya, used essentially topology. Basically, they said, oh, like if you have to have some kind of fermion doubling that happened. So you cannot have a single chiral mode because the band of fermions has to cross somewhere else. I mean, that's roughly what happened. But then they said, oh, they gave a much more rigorous definition of this. But basically, it was just checking how many times a band can cross a single line. It has to be an odd, an even number, etc. That's the simplified version. I don't want to go through the proof of the theorem because I haven't memorized it, but
Okay,
yeah, that's the idea.
Thanks.
Okay. Okay, good. So now let me get into the nitty-gritty. By the way, there are some people in the waiting room. I'm not sure if okay, and anyway, so let me get down into the nitty-gritty here. So I'm going to work with a very specific example, but it can be generalized quite considerably. So this is just for concreteness. So I'm going to start with this very specific theory of free spinless fermions, as I said, in 1+1 dimension, and it's on a lattice. So I'm going to imagine a ring of 2n sites with a specific Hamiltonian, which just involves these kinds of hoppings between fermions. So these are standard fermionic operators that square to 0 and anti-commute on different sites in the usual formulation. And V labels the position. And of course, this is an easy Hamiltonian to diagonalize. You just go to momentum space, and you can rewrite it in terms of these momentum modes, psi kappa. And in particular, I want to stress that I can define. Let me just see if this works. Yeah, I can define this object, the momentum space density or the momentum space occupation number, nk or n kappa, which is going to play an important role in what comes. So I want to stress the notation. And then, of course, this sign just gives you the spectrum of the theory, and you can then choose to populate all the negative energy levels, and you get your standard ground state of this theory. So it's perfectly solvable. Everything is calculable in this theory. And the algebra of operators is generated by a pair of operators on each site, let's say psi and psi dagger, or by a pair of operators at each momentum. That's a nice fact about fermions, that the algebra of operators actually factorizes across momenta. This is actually not something you will get in a generic bosonic system, and this is why I'm talking about fermions. Generalizing to bosons, I have done it, but it has not been published yet. So it's much more involved. I may comment on that later. So these are the two reasonable choices for generators of the algebra. All the other operators can be obtained by taking their products and linear combination. And it's useful to think about what operators are present, what operators are allowed in an algebra, because I'm going to start talking about reducing the number of degrees of freedom on the next slide, as you see here. So a standard way that we imagine going to low energies or long distances, which is sort of an important ingredient of thinking about continuum limit, is Wilsonian renormalization group. So essentially, I'm sure everyone knows how this works. So the idea is you integrate out high momentum modes and you get some effective theory at low momentum. And in a local theory, high momentum translates to high energy, and so you get the low energy theory later. So I'm going to present an algebraic way to talk about this, which is equivalent, just slightly perhaps more unfamiliar, but very useful for what was going to come next. So the algebraic way of formulating Wilsonian energy is as follows. So start from this algebra that I have listed here, this full microscopic algebra, and consider a smaller one, the one that is next to my pointer here, that contains only a subset of operators. So only the operators at momenta that are in some sense near zero and near n. You can see that this is precisely where this spectrum here has nodes, crosses zero, so the energy is close to zero. So that's a very natural choice, and you get two kinds of modes. You get modes near k equals 0 and modes near k equals n, and you impose another cutoff on this new algebra by this number m, which is much smaller than the original number of lattice sites, but is much greater than 1. So you still have a large lattice around. And this m is essentially, the Wilsonian kind of sliding scale. It's the new effective scale of the theory. So this kind of coarse graining precisely removes the high momentum or high energy operators and keeps only the operators that are associated to modes at energies near zero. Is there a question? Yes.
So in this presentation, you're going to fix the filling to be 1/2 the entire time?
I'm actually going to be relatively agnostic. In this particular Hamiltonian, you will have a ground state which has half filling. But as I said, this is just an example, and in principle, everything I say will work for other fillings. That's just not the example I'm working with here.
And what if you don't? You have a chemical potential or something, so you don't know what the filling is. You think something like this would make sense?
I mean, yeah, you can. I mean, if you put a chemical potential, you can still solve the theory, and then you will have some, the Fermi level will have changed or something like that. Or that's going to be, I think, one line on my last slide saying that everything works out when you do that.
Even if you don't know the filling that results from putting your chemical potential.
Right, you're worried that you're worried about this thing that. Sorry, I'm just slow with annotations. You're worried about this kind of particular choice of coarse graining, right? You're saying, what if my nodes are elsewhere or something like that? Yeah, you probably would want to peek at the structure of the UV theory and solve it, because if you're very off, so normally universality saves you, but if you're very off, if your chemical potential is of the order of n, then yeah, then you can be you may get nonsense in the end. So that's something that I assume you have actually figured out, so that you either not let your chemical potential be of order n, or if you do, then you have to change this rule a little bit. But I think that everything is fairly straightforward to do. So it's possible.
Okay, thank you.
Mm-hmm. Thanks for asking. Right. And in general, in fact, the rule that I give here is actually the most general rule for any kind of reduction of subalgebra that describes how you get the effective Hamiltonian. That knows about the dynamics of only the degrees of freedom that are left that are still described by your operator algebra. And the way you do it is the same way you understand reduced density matrices when you compute entanglement entropy or so on. You take a thermal density matrix and you project it. You find the reduced density matrix and you read off the new Hamiltonian from it. In this case, since the theory is free, then this reduced density matrix is also just a tensor product, so it's easy. You just drop the high momentum modes from this Hamiltonian. So I will not comment on this further, but it's good to keep in mind that this is the kind of definition of what I mean by an effective theory. And in particular, if I take the starting theory here, and I reduce this algebra here, I integrate out these high energy modes, then this sign can be approximated just by a linear function. And I will get a Hamiltonian that looks like this. So there's the new cutoff. The spectrum is now just linear. There's no curvature, and I have these two separate momentum density momentum densities, one for momenta near n, one for momenta near 0. This is of course the standard Lattinger model. This is a very long-winded way of describing stuff that has been known for 70 years or so. But it's very good to review it in this way because I'm going to generalize it in a relatively novel way, I think, on the next slide. Good. So this is, so I'm going to, before I talk about this generalization, I'm going to give a very short comment, which is very useful to introduce some notation. So as has been discussed by Susskind in the Hamiltonian formalism, and slightly before him by Kogut and Susskind, the really natural thing to do, especially in 1+1 dimension, is to take these two types of modes at momenta near k and at momenta near k plus n, and to treat them as two different flavors of fermion. So you have one set of fermions at momenta near k and one set of fermions at momenta near n, and you can just think of them as living on a lattice with m sites. The previous one on the previous slide had 2 m sites. I may have not said that, but that was true. I can construct these operators that I described with capital psi and plus and minus, and they will exactly have the right equations of motion to describe to be thought of as chiral modes, as two chiral components of a 2-component spinner. So it's very nice and useful to think about these. And the way they're defined here is through momentum space. So this is the most natural way to define spinors on the lattice. So you start from a larger lattice with spinless fermions, and then you identify different nodes in your band with the different components of your spinors. So this is again an old idea, and this is the kind of stuff that I'm going to be working with in what follows. So, and this is now the new stuff. So now consider taking an even smaller algebra, which has another cutoff that they call Ks. S stands for string. That's kind of cheekily. I always put it with question marks, but it can also stand for smoothness, and as I will describe on this slide. But anyway, there is a cutoff Ks in momentum space that's much smaller than the the inverse of the lattice spacing, or the number of sites, or the size of the Brillouin zone. And what I do with that cutoff is as follows. I consider a smaller algebra of operators where I keep all the fermions at momenta between minus Ks and Ks. This is just a convention, just to make things precise. So I keep those just like I did in the standard Wilsonian RG framework, but I also keep these operators, the densities. They're defined as psi alpha dagger, psi alpha, at every momentum outside of this region. So I don't completely integrate out all the fermions above Ks, but I remove the fermion operators. And so that way, the new algebra has no operators that can cause these densities here to fluctuate. These are central operators of my algebra now. So that's the sort of the different thing that I'm doing compared to standard Wilsonian RG. And as it turns out, this cutoff Ks is actually going to be the second cutoff that I said you need to have. And it's absolutely crucial to have it, because that way you will also be able to talk about the smoothness of fields in position space. So you should think of M as governing how close two field operators can get, and you should think of Ks as giving you sort of a minimal wavelength, which is much greater than the lattice spacing, saying that things have to vary smoothly on length scales of order n over Ks sites. That's what's going to happen. this is just a very natural way to ensure that this happens. And it's possibly not the unique one, but it's definitely the nicest one to work with that I know of. And the natural thing now is to define a projection of these original microscopic operators, psi plus minus, in position space onto this smaller algebra here. And the notation that I will use to define a projection is as follows. So all the lattice operators that I was working with so far had their lattice positions as indices, as subscripts. The projected versions will have their position indices as arguments. That sort of is a very nice, I think, way to emphasize that these are now behaving like continuum operators. And the sense in which they behave like continuum operators is given here. So you can actually check that one by expanding in momentum space, that if you change x by a single lattice spacing, so x is an integer here, so x plus 1 is the site next door. The difference between these two operators is another operator, which I will call d hat psi. And this operator is, in the standard operator norm, very small. So even entry by entry, like all the entries are of order ks over m. Essentially because in Fourier space, you've forbidden individual components of individual momentum modes of psi x to go past ks. And so this way you get an operator equation. You get the sort of constraint which says that nearby operators cannot differ by objects that are greater than ks over m, and that's a small number by construction. So this is how you get smoothly varying operators on the lattice. This is one way to think about getting them. Okay. So now let's explore the consequences of this strange projection. So far I've just given a somewhat nice definition of slowly varying operators, but there is some interesting structure lurking here. And so let me first introduce a little bit more of notation. So if I have an operator which depends on several positions, like so, I will write its smoothing, its projection to this smooth algebra, as follows. So I will just keep all the arguments, but just put them in brackets like here. And the key fact is that if I have a product of two operators, O and O tilde, then the product does not commute with the smoothing, or the smoothing is not a homomorphism. The point is that you can take the product first and then smooth, or vice versa, and you will get two different notions of products on the space of smooth operators by doing so, by choosing whether to smooth first or second. This is really the key fact. This is it may sound trivial, but it's really what's going to give you the OPE structure. And in particular, if we think about our theory of fermions, and we have all of these, and we have a bunch of fermions on the lattice multiplied together, then the way we smooth them is we Fourier transform each of them, and then we look at and then we just in Fourier space just remove those operators which are not allowed. We project them out. And the reason why there is a difference between these two kinds of smoothings is that sometimes when you have two fermion operators, their momentum modes can conspire to multiply into one of these ends that you do have in your algebra. So then those do not get smoothed out; those remain in your expansion, and those end up giving you objects like this. Like they just summing over these momenta ends up giving you some classical numbers, because n and k are classical. They commute with everything, and these c's are precisely going to be the operator product expansion coefficient. and I will show how this is worked out in detail, but this is the idea. And so as oh, there's a question?
Some basic question, is it okay?
Yeah, please.
So I want to understand a few basic things that, because you mentioned the projection and also mentioned the integrate out. And I was wondering, say, whether these two things are necessarily related. And also, when I'm asking a bit more general, and also that maybe I can rephrase after status, and also that sometimes maybe one will do things in the real space, and maybe also you may also do it in the momentum or in this in the energy space. I wonder whether there's some there's some subtlety, or is there some maybe like these slides actually you are doing probably real space, right? Right now you are writing the algebra in this real space.
Yes.
Earlier, I think in the previous slide you are doing momentum.
Yes.
So,
yes.
So but just want to understand that is there some setup that wanted to be.
So I think what you want to, I think the unease that you have is because you kind of need to, I'm kind of using the fact that my theory is free, so that like it's, so the different momentum modes are decoupled. And indeed, I am using that. That's the, so I guess this is a good enough. So the reason why I chose this particular smoothing is precisely because I'm looking at the class of theories which are free, where these NKs commute with the microscopic Hamiltonian. I think that's the key assumption that I'm making. That's not obviously true in a more general interacting theory, and that's why momentum space is special here, or this particular Fourier transform is special here, because these guys here are actually constants of motion. Not only do they commute with all the other operators in the smooth algebra, as I define it, but they also commute with the microscopic Hamiltonian, because in the Lattinger model, all the momenta are non-interacting. So if you had a more general Hamiltonian, which couple different momenta, then you might not be able to do this. Or if you did, you have to prove that there is some sort of universality, that doing this kind of projection will capture something, even if these NKs have to evolve with time. And that's a non-trivial question, which I don't want to discuss now. I have some thoughts on this, but I'm nothing that I can, that I want to go on record with, I guess. So I think that's the non-trivial thing that you may be alluding to here. And now, can you remind me what your first question was?
There's also a question about whether maybe the relation between projection and also integrate out.
Yes, sorry. Okay, good.
Project to lower energy. By integrate out, it seems like you need to integrate high energy modes, but these two procedures may not be the same, right? In general, I suppose.
Oh, you mean, that's right. But in general, I expect that if the microscopic Hamiltonian is local, then then there is some sense in which integrating out does lower energy, the way I defined it. But yeah, like I guess if you have multiple nodes in your space, you need to be aware of. Yeah. So basically, underlying everything I say is the concept that there is some underlying free theory or something that's sufficiently close to a free theory to make sense of everything. And I think that this is not a, if this is a bug, this is also a bug of continuum theories in general. Like we assume that there is, there are things like, canonical commutation relations that work, you start defining a continuum field theory from that. And this is something that in principle is an operator equation that works only as long as you don't have an infinite number of other excitations around or something like that. So this kind of necessity to be somehow, in some sense, near a free theory is, I think, in some ways, a hallmark of continuum QFT, but there's certainly more to this, and I don't have much more to say. So let me defer any further questions on this until the end.
Can I very quickly? I don't want to stop you. So when you say, I missed the beginning of your talk. When you say smooth algebra, you mean like the one that we know in algebra, like 0 is smooth or something, or étal? What do you mean by smooth algebra?
Oh, okay. So when I say smooth algebra, I mean something that I actually defined here. So it's this algebra here. Oh, sorry. It's this algebra here. And it's smooth in the sense that I can actually show that once I project my position space operators to this algebra, as you see here, they actually obey relations between different sites. So operators on two different sites actually have to differ by a small amount. And in that sense, I call it smooth.
Okay.
So it's not. I did not have any allusion to anything else.
Okay. All right. Got it. Thanks.
You're welcome. Okay. Good. So.
Sorry, Djordje. I still want to ask you about this thing at the end of page 6 because I feel like I'm in danger of missing the main point. So
Okay.
This identity that you got at the end of page 6, which is exactly the point you were just talking about. Could you tell me a little bit more why that's true? Because to me, it sounds like you're saying it doesn't fluctuate very much, which sounds like it's saying you don't have very high momentum modes. But it's M that controls whether you have those high momentum modes or not KS. So I'm getting confused about the difference between them.
Okay, so I will try to say it here, and then if necessary, I might have to go to a whiteboard. I think so. Check out these definitions of let's work with psi plus. So check out this definition of psi plus, and ask what happens when you project it to this smaller algebra here. So essentially, what happens is that the projection is very simple. You basically replace these the bounds in the sum with minus ks and ks minus 1, because those are the only operators, those are the only psi k's that you have left in your algebra. Okay.
Okay.
And then imagine moving, changing x to x plus 1.
Okay.
So here in the exponent you will have x plus 1, and so that means that and so you can expand this exponent in 1, that 1 is the delta x, times k over m. And because the k in the sum only goes up to ks, you're guaranteed that this is a small parameter, this k over m. So,
okay. Yeah.
So it bounds. So the size of the correction, the size of the difference between psi x plus 1 and psi x in the smoothed, in the projected sense, has to be bounded by some by a bunch of operators, by a sum of operators with a prefactor. Each, these psi k's all have entries order 1, and then there is a prefactor that's bounded by ks over m in front of it.
Yeah. So okay. I mean, fine, I guess. Yeah. I mean, to me, it sounds like again you're just like cutting off high momentum modes, and I don't really understand the difference. Okay, sorry, here's another question. In that second bullet point on your slide, when you defined the smooth subalgebra,
yes,
what would have happened if you didn't have the NK alphas, if your subalgebra were just that first part?
Perfect. So what would happen is precisely what I said on the previous slide when I talked about Wilsonian RG. So, KS would have become the new, M would have become KS. So I would have
no, that's what I thought. I thought you would just be doing the Wilsonian RG more to reduce M down to KS, but if you do the same analysis, I think that third thing, like the bottom, it's still true. It's suppressed by KS over M, and that's just because you defined the spinners.
No, you're absolutely right. Yeah, I understand why you're saying that. But the important thing is that the difference between the two approaches is that you do not get this structure, because if you don't have any operators, if you don't have any operators at
yeah, no, I certainly agree that you don't get any OPE, because it'll just be trivial. Then it will commute.
Yes.
But that's not a good reason to explain why I'm like what KS is in the first place, or why that was the right projection to take. And I still don't have a good intuitive sense of what the difference is between KS and M.
Okay, good. So okay, so let's see. So I think the practical differences will become clearer, you know, in the rest of the talk when I start giving calculations. But I think that I think what I said on the previous slide is already a good preview. So basically what happens is that basically what I'm saying is that the way I did this, the way I set this up is that I can talk about operators that are you know, close to each other, but I cannot talk about them being completely independent. So this sort of introduces, and this is one way. I'm not saying that this is necessarily the best way, but it's, I'm definitely not saying this is the only way to define a smooth algebra or something that works the way I want it to, but it's definitely the nicest one to calculate with that I know of. So basically what happens is that you impose these relations, and these are going to act as sort of, you know, gauge constraints in some sense. Like, you know, your operators at x and x+1 are no longer independent of each other.
Right.
But you know, they'll give you some microscopic entanglement that's necessary. You know that these are these statements that you see in continuum theory, which says that, you know, entanglement entropy has to be infinite because you have infinite entanglement at microscopic scales. Sure. This is sort of what tells you where you get that entanglement from. And it's governed by this Ks over M. Another way to say it, which I will get to in a moment, is that Ks over M, or its inverse rather, sets up as a length scale such that you know, any two operators that get within that length scale of each other can be expanded in an operator product expansion. You know, that's sort of the way you ended up getting, you know, a meaningful operator product expansion. If they're far away from each other, these operators psi of x are essentially smeared. So
I see. Okay.
And the smearing is set by this Ks.
Okay, fantastic. Like for a while, I was confused about the smoothness thing, because smoothness or regularity is, of course, just related to decay in Fourier space. So I was like, yeah, of course, you're just integrating out. How's that different from Wilsonian RG? But I think this point, like motivating it by the fact that I want an OPE when two operators get close to each other, makes it clear I have to do this.
Yes, exactly. And as it turns out, as I mentioned already, like pretty much everything else that I can think of that, you know, we like, all the structures we like in like QFT will end up emerging from having this extra cutoff. So I will mention that in a second. Good. Okay.
May I ask another question? So you mentioned in the beginning that some lattice model does not have a continuum limit unless it's close to second order phase transition. Is that also related to this phenomenon?
No, not necessarily, I would say. I would say that that's really related to the fact that, you know, if you're near a critical point, if you're near a phase transition, then your correlation functions will explode. Your correlation lengths will become very large compared to the lattice spacing, and that's sort of the intuitive, you know, intuitively that has to happen if you want to have you know, macroscopically large correlations. Otherwise, if you're in a very gapped state in terms of the lattice theory, like if you're in a very massive phase or something, then you're not guaranteed that you will get like a, you know, a universal theory which does not depend on your cutoff, with like a correlation length which is like just a number of size 1. That's why you needed to be near a critical point to make sure that your correlation lengths are sufficiently large. But you know, there are other examples. Like for instance, if you go into if you take a gauge theory, I'm not really going to talk about gauge theories here, but if you go to a gauge theory and go deep in the deconfined limit, in the topological limit, then you can expect that even that topological limit, which is far away from a critical point, will still be described by a continuum theory. So it's just going to be a slightly different, it's going to be a TQFT, not something that we normally talk about. But that will happen as well, and that's because in a preconfined limit like that, you will actually also end up getting very large correlation length. So yeah, so that's why I said so. But I feel that that's a sort of or slightly orthogonal question to this. So what I'm giving you on this slide is actually something that works even if the theory is gapped. And what's going to happen if, depending on whether my theory is, mass gapless or gapped, is that these coefficients here, these C's, will differ. And that's because the expectation values for NKs will differ. Because if the theory is gapless, then typically the NKs below the Dirac C will remain populated. Whereas if the theory is gapped, you can imagine that you really do not allow any fermions, for instance, or something like that. So things will change. The values of these guys, NK, will change, and therefore all these coefficients will change, but the procedure of defining the smooth theory will not change, even if you're not near a critical point. So it's a good question. It's the point is that what I said will define OPE coefficients even far away from critical point.
Okay, thank you.
Mm-hmm. Good. And so let me say a little bit more about this smooth algebra. I already kind of said some of these things. So this is the definition, and what I want to contrast this with the way that this is normally phrased in CFT textbooks or string theory textbooks. So normally, I'm writing this formula in red because the notation is not consistent with the rest of my notation. This is just the standard way you will see it in the literature. So the way a singular part of an OPE is usually denoted in a continuum theory, in the literature, is as follows. So you say, oh, I have this product of operators which can have some singularities, and then I subtract the normal ordered, so-called normal ordered product, which sort of subtracts off the finite pieces. And there are multiple ways to define what you mean by normal ordering, but essentially this is the and depending on which theory you're talking about, you use a different definition of this. But this is how you normally define it, and this is you can compare this. You can compare these two relations. They're analogous to each other. But our relation is slightly more general because we are also talking about smoothing out individual operators, not just talking about smoothing, like getting the singular parts from products of operators. And also, what we are doing is that we are actually specifying that you really do need this KS. So in some definitions of normal ordering, when you say, oh, just put all the creation operators to the left of all the annihilation operators, that works in some situations, but it's not very precise. And one way that you can see that it's not precise is that it doesn't actually take into account this cutoff KS. Essentially, the way it should be phrased is put all the creation operators at momenta below KS to the left of each other in some prescribed order. That's sort of always implicit in the literature, but in here I'm making it fully explicit. And then the second comment that I wanted to make is something already I think replied to Arnav with. So I've defined smoothing in momentum space, but I can just sort of do the Fourier transform twice, and I can re-express the smooth operator, any smooth operator OX, in terms of its lattice versions OY. And I can think of it as just sort of being smeared, being weighted with some smearing function, which is some Gaussian, which oscillates a little bit, and decays at a length scale of m over k, of m over ks. So normally, when you say continuum QFT, oh, there's some need to define operators as smeared objects. And this is sort of how you get that smearing from the lattice. Again, you can choose different smearing conventions, and you should get similar results. And as I mentioned already, you also do not need...
Can I ask you another quick question?
Yeah, sure.
Your differential operator in the previous stage, when you define the smooth algebra, is d square equal to 0?
Oh.
Del bar, del hat.
Okay, good, excellent. So not quite. So I didn't even go through this, and this is the technical detail. In general, for every operator, I want to say this: you have to be very careful about its powers, because the powers may get contaminated. You know, like as you take higher and higher powers, then like you have to worry about this expansion. You know, there may be terms that you are missing. So that's one thing I need to state. And then the other thing I should also state is that this d hat, I'm debating whether to even talk about this technicality now, but let me just say that just think of this d hat psi, don't think of d hat as an operator. Just think of d hat psi in this context as the difference between these two, and this difference is something that's small.
Yeah, because if you really think about it even as an operator, then it actually, your definition of a smooth algebra does match with the definition of a smooth or a tall algebra in algebra.
That's good.
Yeah. So basically, you're looking at ideal of elements which look like d hat psi, and if they actually square to 0, then you can define a smooth algebra based on some kind of a lifting property. So,
okay.
Maybe it's relevant to that, but here your del hat is not equal. It doesn't square to 0, but maybe to some degree, actually, eventually.
Right. I mean, d hat definitely squares to something that's of order ks squared over m squared, and therefore, in some sense, you can approximately say it's 0.
Okay.
But yeah, I'm not familiar with that particular.
Okay.
We'll talk about that more.
Thanks. Sorry.
No, okay. Let me just give at least elementary examples, and then let people go, because I'm essentially running out of time. But if people want, I can stay on later and talk. But yeah, let me just so this is how I define this lack of commutativity between smoothing and taking products, as I at the top of the page, as shown at the top of the page here. And so now I can actually say, okay, so what does this actually look like? You know, to what extent does this reproduce known OPE expressions? And you know, we can do it for in the free theory very simply. So we can do it for individual fermion operators. The only non-zero, the only contribution to this product is comes from the fact that some modes in the ground state in the Dirac sea are occupied. So some of the nks are equal to 1 in some part of the momentum space. And so you can work it out, and you will see that you get a function that precisely goes as, you know, 1 over I times the distance plus corrections. So you will see that if the distance of two operators is greater than m over ks, then you can no longer ignore these corrections. And then, you know, this standard statement that you have an OPE coefficient, you know, an OPE product, which is like the identity operator over a singular term over y minus x, that has to be corrected as you go past this smearing line. So the standard OPEs that you see in the literature kind of always assume that you've taken your operators to be within m over ks of each other, that in terms of the lattice. So that's one comment. And then the other comment that I have also promised to talk about is that what happens with currents. So I can define currents, the chiral currents, so essentially the density of each fermion, each component of the fermion in position space, as so. And I can compute their OPEs as well. And you know, I will get the standard OPE. You know, I will get something that goes as, you know, y minus x squared plus these corrections. But there's something interesting that happens with these guys. So basically, the way I phrase this is that you know, the singular terms, these interesting y minus x terms, are all contained only in the OP coefficients. They're not contained in the correlations of individual smeared operators. Essentially, what you want to say is that when you have smeared operators and you take them to be within a smearing length of each other, then they should not have any interesting correlations. You've kind of removed all the UV stuff, so you should not have any interesting correlations. This is a great example which shows that if this does not happen, if indeed you actually do have some non-trivial correlation between smooth operators at distances smaller than this scale m over ks, then there's some RG invariant, let's say. You have something non-trivial happening in the IR of the theory. And in this case, it's very well known what happens. So it's the fact that there exists a chiral anomaly in this theory. And so you can compute the correlator of you can really compute the expectation value of the commutator in the ground state of two currents, and you will get that it essentially behaves as a derivative of a delta function, which is the standard position space expression for the Kac-Moody algebra. This is even more interesting in momentum space. I did not write it here, but I can possibly write it now. So the point is that in momentum space, you will have things like this. You will have, you will have something like this, plus L. You will have a correlation function that goes as dk minus L. And there will be a function that looks like k only at k less than kf. So this is what you normally, and there might be some constant here. So this is normally how you express the Kac-Moody algebra in momentum space. But the interesting thing is that this function here will actually get corrections as k goes above ks. So what happens is that this function will actually look like this. If this is ks and this is 2ks, this function here actually looks like this. It goes linearly up to ks and then decays linearly up to 2ks, and and then it's just 0 from there on. So this is something that you can work out the ks corrections here, and this is the sort of the correction, the way the lattice sort of regularizes this, because clearly this function couldn't just keep going to infinity on a lattice. So you can actually get corrections to the standard behavior by knowing that there is this extra cut of ks. These corrections have nothing to do with m. They have nothing to do with the lattice spacing. These corrections are all at ks. So that's one. And you can kind of see, like, if you try to construct a Kac-Moody algebra, as I mentioned already, if you try to construct it directly from the lattice, you can kind of see that putting a cutoff at the scale of m does not help. You kind of need something else. And this is what this current approach gives you. So this is how it works. This is how you end up, phrasing the existence of non-trivial current algebras and interesting OPEs in terms of lattice operators. So everything I computed was starting from a lattice theory. I just used the smooth algebra as sort of the guiding principle to tell me, which operators to look at. I will not go through this in any way. Okay, I guess we need to clean this. Okay. I will not go through this in any way, but I will just mention that I can do the same kind of calculation to find the OPs in the Ising CFT, because that's some spin system that can be dualized to a fermion theory. It's not a free Dirac fermion, as we've discussed so far, but it's a free Majorana fermion. And essentially what happens is that you see that a bunch of operators will smooth to the identity. And the ones that do not end up smoothing to the identity end up smoothing to precisely the primaries or descendants of that we know from the Ising CFT. And this is a relatively involved calculation. but you can actually see that you can, but you will actually, using the definitions that I gave you, you can actually extract the right OP coefficients. And of course, the right scaling dimensions, but also the right OP coefficients here. So I will not go through this because I don't want to keep people from leaving if they want to or seeing the punchlines. But let me just say that this has been worked out and ends up working really nicely. So so it's nice to have a sanity check to see that this proposed definition for OPs starting from a lattice can actually be connected to known CFT results in a very nice and non-trivial way. So I will just close by making a few comments about generalization. So everything I said actually generalizes fairly nicely to higher dimensions. You just have to be a bit, juggle a few more indices or a few more non-trivial bits. But in principle, it generalizes nicely. So you can actually see the the 4-dimensional chiral anomaly, or you can see the 3-dimensional. There you don't have anomalies, but you have contact terms between currents. So you can actually show that the contact terms will also depend on the smoothness scale. They will depend on Ks, the same way that the Kac-Moody, the non-trivial commutator of currents, depended on the so-called Schwinger term, depended on Ks. You can now consider all sorts of perturbations. You can think of the Ising model, I guess, as one perturbation of the Dirac fermion. And you can add chemical potentials, masses, and all sorts of smooth interactions. And that will lead you to a calculable change of OP coefficients. So nothing in the procedure will change as long as the Hamiltonian keeps, as long as the Hamiltonian is modified only by smooth operators. As long as these NKs remain constants of motion. And this is the way that people study, for instance, bosonization. They add a current coupling, but they make it normal ordered. Or in my terms, they add a product of two smooth currents, and that ends up giving you being that way you can start talking about interacting Hamiltonians that can be dualized only in the smooth regime to some bosonic Hamiltonians, which are interesting. This is also something that I've written about in the first of the 2 papers that I mentioned at the beginning. So as I said, so the punchline is that if you have any smooth deformation, in principle, you can understand the new OP coefficients and the new algebras, etc., in this new theory, using the same methods given here. On the other hand, if you add microscopic couplings, if you have some more non-trivial theory, then things get dicier, and it's possible that the kind of smoothing out that I defined here will give you some universal data, but it's not going to be as elegant as I think this is. The other important thing to emphasize is that the same story will actually hold for scalar theories, except it's going to get progressively more complicated, because scalar theories don't just have one large on the lattice. Don't just have one large parameter, which is like the number of lattice sites. They also have large parameters coming from the fact that they're on each site they have a very large Hilbert space. So you actually need to regularize that one as well, and you end up needing to have to put in smoothness regulators for the target space as well. So this is something that I have worked out, and that gives you a very nice way of defining vertex operator algebras, for instance, in 1+1 dimensional scalar theory. But this is something that I definitely do not have time to talk about now, and I'm happy to continue by email. And then, of course, there's many other questions you can ask. You can ask, okay, how do you see the Virasoro algebra arising? How do you talk about gauging a particular symmetry? How do you see your favorite continuum thing? So I think that all of these questions can be given some answers, or can at least be given a lattice understanding using this approach. And in particular, what I think is very interesting is to ask whether there is a way to think about, trying to possibly measure Ks, or trying to see if it would actually, if you have some particle scattering, will it actually influence the kinds of things you can measure? Because it certainly influences, let's say, the Kac-Moody algebra, so it can probably influence a lot of other things. So that's sort of the punchline here. And with that, I want to thank you for the attention, and sorry for running over time. And I'll still be around, so feel free to ask me more questions. Thanks.
So are there any more questions?
I have one.
Yeah.
So it's maybe also related to previous long discussion also with other people, is that suppose you try to integrate out some high energy modes, and in some case maybe the high energy modes may be labeled by some higher momentums can still theory that the high energy modes interact with low energy. This may not be obvious for continuum field theory point of view, but like in condensed matter system, like people consider more exotic pairing of fermion-fermion interactions. You can have something like pairing even carry momentums, and different momentum may interact. So I can theory that the high energy momentum modes may not be decoupled from low energy modes, and that's related to some discussion in your talk earlier. But if we integrate out some high energy modes, maybe that the new theory that you integrate out may not be the same as the theory that you project. And certainly these are not directly related to what you develop, but I wonder whether you have any thoughts on that type of theory. And for the case that the high energy modes may not be decoupled from low energy, and when you try to
yeah, no, that's a good point. I mean, that's I think the main conceptual limitation of what I said, which is that in those cases you kind of have to rely on a miracle of universality to say, oh, somehow my long distance behavior will somehow still be described by something that's smooth, and that will approximately hold in this algebra. This did not be the case in general, and I don't know how to make this precise. I don't know how to say, okay, this theory will have the right a nice low energy behavior if I start coupling different momentum modes, and this theory will not. Yeah, so I don't have anything deep to say. Like, I have some thoughts, but I don't think they're well formed enough for me to actually go on a limb and say them. So yeah, I think that's an open question.
It seems interesting to also think those type of theories, right? And another question is that when you do OPE, like for the fermions, it looks you are trying to convert between the description on the lattice and description on the continuum. And on the lattice, I think most of them, we treat the fermion operators as a two-dimensional Hilbert space and with anti-commutation relations.
Yes.
Continuum, it looks like we usually give fermion more structures. In a lattice, usually it could be just discrete, and also it could be just non-relativistic. But there are more structures, and I wonder whether the relations you relate the two actually also capture the difference. Certainly, you didn't map one to the other. There are some kind of OPE and some expansion terms. I wonder whether this type of maybe additional structure from a continuum can be captured in this. These are just some.
Yeah. So the entire point is that if you have operators like this psi of x, then in general they can obey interesting constraints. So I can imagine taking a product of many psis at a given point, or like at nearby points, and then they're somehow related to each other. There's because psi varies so slowly on the lattice scale, you will indeed get that in some sense like within a single smearing length, all the fermions there behave as one fermion. But nevertheless, the underlying Hilbert space is really, you know, large. It's not just two-dimensional, because there is a two-dimensional Hilbert space at each point within the smearing scale. So indeed, you get some extra structure, and you have to worry what happens when you take large numbers of products of these guys, because then these kinds of expansions will not work. As I mentioned already, like if you take a product of many fermions, then you can't just maybe end at the first order term. You have to add more terms and so on. So my point is that indeed the smearing sort of makes operators seem similar to each other and gives you extra product structure that was never obvious on the lattice. And I think that, you know, as the OPEs capture some of that product structure, and I think that's the easiest thing to compare for now. But there's, you know, in general, more stuff. And if you have ideas, I can talk to you about them.
Maybe the slide fermion OP previous, maybe I think 7, 7.
7, okay.
So is that correct? That if you look at the example E2 there, the left hand side is the lattice, which you can even take non-relativistic fermion. On the right hand side, usually can be relativistic fermion.
Well, right. I mean, yeah. Essentially, these objects all are essentially continuum fields. But you know, the point I want to stress is that I have defined all of them from the lattice, and this inequality here precisely says that, you know, these smooth. You need to be careful about what you mean by a product of smooth fields, because there's definitely different ways to define a product of smooth fields, taking into account different amounts of, you know, singular structure, the UV structure. Yeah, so in some sense, this is precisely the correspondence between the, you know, the lattice and the continuum, and it also tells you, tells you how the lattice resolves some of the ambiguities that we are normally facing in the continuum, like what does a product of operators mean? So yeah, I think that's what you want to say. Are there any other questions?
If there are no other questions, then maybe we can all unmute our microphones and thank the speaker.
Thank you very much.
Thank you.
Okay, thanks, everyone.